All right, I have some functions up here, and there's a really important property, a really important principle we need to sort of develop here. So I'm going to start with something that you're a little more familiar with, the ordinary cube function and the ordinary cube root function. You're pretty familiar with those. If I want to take f of, in this case, if I want to take f of 5 to the third power is 125. If I want to take f inverse of, let's say, 8, the third root of 8 is 2. So these are computations you're familiar with. These are a little more gnarly, so let's leave those for a little bit. We're going to argue sort of by analogy here. But suppose we take, something that's pretty straightforward to use. Suppose I use x equals 2. Remember what we actually have here is we have f maps domain A to range B. So here's the domain, there's the range. So f, if there's 2 in this set, f of 2, 2 to the third power, goes to 8. But f inverse, in order to be the inverse, remember the inverse returns these values back where they started from. And so what we can say is f of 2 is equal to 8. So anywhere you see 8, you may take 8 out of the expression and put in the symbols f of 2. Those are interchangeable for this notion, for this problem. Well, f inverse says this. If I start with domain here, the domain is B and the range is A. This is domain and here's range. But here, this is the domain, this is the range. And so f inverse takes the domain from this set, the domain element from this set, and maps it back to the original value it came from. So f inverse just reverses the process. So f inverse would say, if I want to take 8, f inverse of 8, the third root of 8, well, we know the third root of 8. Third root of 8 is 2. And so what we may say is f inverse of 8 is equal to 2. All right? Now, what is this the same thing as saying? This is the same thing that, remember, we said it just a second ago. Just a moment ago, we said anywhere you see 8, you may take it out, and in its place, put f of 2. So I'm going to take 8 out of here and put this in there and see what it looks like. If I take 8 out and put this stuff in its place, then what you generate, what it would look like is f inverse of, what would go in here, not 8, what would go in here is that expression, f of 2. But the key is that's still equal to 2. So this is the key element. This is it. This is what we're looking for. If you apply inverse functions in sequence, it is as if they cancel. F inverse and f cancel, and you're left with 2. If you apply inverse functions in sequence, the result is the argument. If you apply inverse functions in sequence, the result is the argument. Now that's true whether you compute them. It's also true even if you don't compute them. And so I don't need to actually do the computation. We know that if you take f, now if x is 2, it's not very hard to compute 2 to the third. If x is 5, it's not very hard. But even if x is more challenging to compute, 48, now if I had a calculator I could compute it, but the point is this, whatever that number works out to be, you start with 48, map it over to here. F of 48 is so here's 48, and here's some number, we don't know what it is. But we know that if you take that result and immediately compute f inverse, now we are here. If you apply inverse functions in sequence, they cancel, you're left with just the argument. What is f inverse of f of 48? It's the same principle. F inverse of f of 2 is equal to 2. So f inverse of f of 48 is equal to 48. And there's nothing magic about 48. This is true. If I take f inverse of f of, put any number you want, a 16.1, I know what that is because these cancel, you're left with 16.1. So any value in this domain, this will work sufficient. This will work fine. When you apply inverse functions in sequence, they cancel. Now, this is true certainly if you do f first and f inverse second. Remember, we work from the inside out. But this is also true if you do f inverse first? What is the third root of, pick a number out of the blue sky, 119. Take the f inverse of 119, but then immediately apply f to that. We apply these functions in sequence. F inverse, the third root of 119, if you had a calculator you could find it. But the point is this, whatever that is, when you take that and immediately apply f, now what we're doing is this. We're taking 119 here, applying f inverse and getting something we don't know over here, but then immediately evaluating that at f, that goes back to the original 119. So the principle is, when you apply inverse functions in sequence, they cancel, you're left with the argument. When you apply inverse functions in sequence, they cancel, you're left with the argument. That's true of these inverse functions. That's also true of these inverse functions. So even if you don't know what the numbers are, even if you, see the point is we don't need to compute this specific value. You know that if, again this is a big if you compute f of a number and then immediately before you do anything else, apply the inverse. Applying a function and the inverse immediately in succession, they cancel, you're left with just the argument. And the key is log base 5 and 5 to the x, these are inverse functions. And so if we take g of, pick any number you want to pick, 19, g of 19, that is, if I took 5 and raised it to the 19th power, that would be a gigantically huge number. If you had a calculator, you could find it. But if you take that number, whatever it is, and then immediately take the g inverse of that, when you apply inverse functions in sequence, they cancel. What is this result going to be? Yes, that result's going to be 19, because when you apply inverse functions in sequence, they cancel. Now, let's write this using this notation. When I say g of 19, what do I mean? When I say g of 19, what that means is 5 raised to the 19th power. That's what that means. And when okay, so that means I want g inverse of. What is g of 19? G of 19 is that. All right? Now, when I say take g inverse of something, when I take g inverse of stuff, when I say g inverse of stuff, what is that? The stuff goes in here. That becomes log base 5 of the stuff. All right? Log base 5. And so when I say g inverse of this stuff, that's the same thing as saying log base 5 of this stuff. But what did we say that was originally? That's 19. This gives rise to our next principle. There's nothing magic about log base 5 and 5 to the x. We could have started with 6 to the x and log base 6. We could have started with 9 to the x and log base 9. We could have started with any base. This would have still been the case. When you apply an exponential and then a logarithm immediately in sequence, that's the key, immediately. If you apply exponential and logarithms in sequence, they cancel, and the result is the argument. So we can now expand this to a larger property or a larger principle. So if we take log base, there's nothing magic about 5. It can be anything. Log base, I don't care what it is. Log base 5 of, or log base b of, this can be any value. By 5 is allowed to be any base. What is that equal to? It's equal to that exponent. When you apply logarithm and exponential in sequence, the result is that value. So log base b of b to the x is equal to x. Log base b of e to the x is equal to the x. When you apply them in sequence, they cancel. When you apply them in sequence, they cancel. What is log? So let's do a specific case. Come on. Log base 4 of 4 to the x is equal to x, because logarithm and exponential cancel out, you're left with just the argument. Logarithm and exponential cancel out, you're left with just the argument. All right? Log base 4 of 9 to the x. I'm sorry, they have to be the same thing. Log base 9 of 9 to the x. Log base 9 of 9 to the x. They cancel, you're left with just x. When you apply logarithm and exponential in sequence, it is as if they cancel. And there's nothing magic about this being a specific value. So let's write this larger property here. This is not the way you're going to see this in a textbook, but this is a way to think of it. Log base b of b raised to the stuff. Log base b of b raised to the stuff. The logarithm and the exponential cancel. Now the stuff can be a single number, it can be a single variable, it can be a larger expression. So let's apply this property. Log base b of b raised to the 4x plus 6. Log base b of b to the stuff. What does that give us? That gives us the stuff. That gives us the 4x plus 6. What is log? Now, the b can be any value. Now, one thing is, they must match. They must match. If they don't match, then this doesn't simplify in this method. So I can take log base, let's say log base 7 of 7 raised to the power of x squared plus 1. Logarithm exponential cancel. You're left with just the argument, x squared plus 1. Log base 10 of 10 raised to the x minus 4x squared. Log base b of b to the x. As long as these bases match, the logarithm and the exponential cancel, you're left with, there should be a parenthesis, x minus 4x squared. And the key is log base b of b to the stuff. If the bases don't match, then it doesn't simplify. If we have log base 5 of 4 raised to the x plus 1, this does not simplify using this procedure. Do nothing. This doesn't simplify. The bases must match. The bases can be fractions. We can do log base 1/2 of 1/2 raised to the x minus 1. As long as the bases match, logarithm, exponential cancel, you're left with the x minus 1. All right? So when you apply inverse functions in sequence, they cancel. Log of exponential raised to a power. Log base b of b to the stuff is equal to the stuff.